This video shows the derivation of some common constant acceleration kinematic equations. You'll see some of the equations that we've seen before when we did our motion analysis. This just goes about it a different way and shows how we might interpret it differently by using area under the velocity versus time graph. I'll start with analogy with constant velocity, just to kind of show how to take the area under the graph and how that translates to a displacement. So if we were looking at a graph or had a model of motion that was constant velocity, which is how we started our study of motion, we'd have a velocity versus time graph with a constant value. What we studied is how if you took a time interval, a delta t in between t initial and t final, that the area under that graph would have some physical meaning. What we showed in class is that multiplying the base times the height, which is the area of any rectangle, actually has some physical meaning on our system here. So this displacement, the interval between these two times shown here would be the base, and then the height would be the value of v, which is a constant. And when we multiply those things, we get the interval times the velocity, or as we often show it as just v delta t. The point of this whole thing is that that area represents the displacement over that time interval. And now we have an equation to find the displacement over that time interval. Now this is something we would have known just by rearranging our definition of velocity, and we've used this a couple times, but this is just kind of showing it in a different way, that this equation, which is just an algebraic remanipulation of this, also has some physical meaning on our graph. So how could we use that? Well, if we had a position versus time graph, and we happen to know the initial position, over that same time interval, we could apply that displacement, and therefore an initial position plus a displacement allows us to know the final position as well. In this case, we know that that's going to be a linear model, so we can just kind of connect those lines. So we did that back in the constant velocity part, but now I want to show that for changing velocity. We'll start with just constant acceleration from rest. This is a linear model, and that's the equation we've been using. In this case, since it's from rest, this v naught, or initial velocity term, would be 0, and then we just have v final equals at. We do the same thing where we choose a time interval, and then we picture the area under that graph. In this case, a triangle, whose area would be 1/2 base times height. The height of the triangle is going to be given by v final, and we'll kind of show how to work that into the equation eventually. I'm going to really just take a time out here and talk about the difference between delta t and t. In general, we could derive these equations for any interval delta t from t initial to t final. But in some of these equations, we would just put t initial equals 0, and then in that case t final just becomes the value of t. You might notice some similar kinematic equations, ones that are derived in terms of 0 to t and some that are derived in terms of t initial to t final. So some of them might be in terms of delta t and some of them might be in terms of just t, and you kind of got to think about why that's more or less the same approach. Are you talking about a start from 0 on the clock to t, or delta t, any delta t? So in this case, it's a little bit more common to use 0 to t. Later on, I'm actually going to switch back to the other notation just to derive what's most common for that particular equation. So here, using these 0 to t, we would say the base then is t minus 0, or just t, and then the height is v final. This is a correct equation, but you don't frequently see it in this form. What's often done is then to use the v final, the actual equation of the line, to plug in for there, and then realizing that that would be at. So this is the equation of the line, and then this t comes from here. Now we've got an equation, and repeating the big idea is that the area under this graph gives us the displacement, and now we have an equation for the displacement. And so you'll see this equation pretty frequently, and we've actually seen this equation before. If you look on our AP equation sheet or the equations we've been using for this graph, this is what's on there. If we subtract this final position minus this initial position, we get a displacement. That's the displacement. And in this case, since the object is traveling from rest, this term drops out. So we've seen this equation before. This is just another way to show it on a v versus t graph. How could you use that? Well, if you had a position versus time graph and you happen to know what the initial position was, after some time interval, we would know that the area under the graph, which equals the displacement, gives us the change in the position. And now we know the final position. You couldn't just draw a line in between them, though. You would have to know something about the actual motion. In this case, since it's a constant acceleration from rest, we would start with a slope of 0 and then curve upwards to a final position. And that's what it looks like. What if it's not from rest? What if instead we have an initial value of v? It's a little bit more complex this way, and now this v naught term is not going to drop out to 0. But we could look at the same interval. And this is the equation of the line here. The reason I'm writing this in this way is because I'm going to use some of this notation later. You'll kind of note that these are basically the same equation, whether we call this v at a given time or v final. I just wanted to use that notation so I didn't say just v when I'm deriving these equations. But this is not an easy shape to take just one single area of, but it is much easier to break it into two areas, one that's a rectangle and one that's a triangle. And then we just add, to get the total area, we add the area of the two of them. First one is area 1 is 1/2 base times height. Keep in mind these are the same base, but their heights may be different, right? So both of these are the same base. In this picture, it looks like the heights are similar, but they certainly don't have to be. So let's explain this a little bit. The base is t minus 0, right, or just t. And the height of the triangle is v final minus v initial. So that's just this height right there, okay? The area of the rectangle would be the same base, t, or t minus 0, times v naught, or the initial velocity. So that's this area right there, and that's that term. Okay. Now this would be a correct expression, but we don't usually keep it like this. We usually keep it in terms, we try to put it in terms of something else by replacing the VF. We replace the VF with the equation of this line. And that gives us, very similar to what we had last time, this AT term. Big idea is that the total area under the graph is the displacement, and now we have an equation for that displacement. You'll notice another similarity to the equation from the previous slide. We would use this in the same way. If we had an initial position after that time interval for which we found the area under the graph, we could apply that displacement, thus finding the new final position after that interval. And then when we're going to draw the graph in, we realize that it's also going to be curving upwards because we've got a positive acceleration, but instead we can't start with a slope of 0 because a slope of 0 would be starting at rest. We have to start with a positive slope because this is an initial positive value. And there you go. There's an alternate way to do this. It's a little bit, I don't know, not something you would immediately think of, but once you use the equation, you can find that it's really very useful for certain situations. So it's just a different way when the initial velocity doesn't equal 0. So if we have this graph like this, that's the equation, that's the time interval. A different way to look at that area, oh, and I'm just rewriting this because I'm going to go back to the delta t notation just because it's more common for this derivation and not some ti and tf and not 0 and t. But if we envision this area here as having the same base but a height of the average velocity, and that works because this is linear, we can kind of see that the air, really you're saying, but this is the area under the graph right here. But this little piece, this little triangle right here is actually the same as this triangle. So this actual shape and the area of this rectangle that I've shown are actually equal. Then it becomes just an easy rectangle. Area equals base times height. The base is simply the delta t here, and the height is this average velocity, and we'll just have to use the expression for average velocity. So t, this interval I've rewritten as delta t, and now obviously the average velocity is just the average. This is the equation for the average of the two. I'm going to rearrange this, but the big idea is that the area under this graph gives the displacement over that same interval, and just rearranging, I get 1/2 and then v naught plus vf times delta t. This is not on your AP equation sheet, but ends up being an exceptionally useful equation sometimes when the other ones don't seem to work, or that you can't do the other ones in just one step. This one can be very useful. So you use that in the same way. If we had an initial position, and then after that same time interval over which we found the area under the graph, we could apply that displacement, we would know the final position, and then we could just insert the accelerating motion model that curves upward and starts with an initial velocity of not 0, shown by a non-zero slope here.